next law we're going to look at is called Charles's Law. Charles's Law. The formula you will see in a textbook or in the internet would look like this here. And I don't like to use that formula. I think that makes the math more complex. You may disagree, but that's okay. So all I've done is rearranged the lighter blue down here into this. So if you just solve for a singular line, this would be the same algebra. So I'm going to institute this formula or use this formula as I proceed through here. We're going to do some calculations and then look at the patterns. So you should be in gas law notes, and you should be on the page that starts with example 9, Charles's Law. You will see at the top the formula, standard pressures, and also you will see temperature conversions. All right, before we get started on doing any calculations, I want to look at this formula for just a moment. And I want to talk about the fact that I have V1 but T2. That's the only thing that makes this confusing, is that the T's and the V subscript numbers are different, okay? The formula is different, but the labeling process is the same. So the formula, notice I have V1T2 equals V2T1. Very important that you understand that's how the formula must go. The T temperature always has the opposite subscript of what it's next to in these calculations. Okay, meaning that this is a 1 and therefore that's a 2, because its temperature has to be the difficult variable. Okay. So as I look at number 9, I'm going to read through and label things. I labeled this as my volume and this as my temperature. And then I kept reading and I came across another volume. How did I know this first one was volume? Because of liters. And I knew this was temperature because of degrees Celsius. They're together, so I decided to make them 1s. Technically, I could have made them 2s, but it makes more sense as I read this word problem to make them 1s. I am going to then see what happens when I get to this new volume. Okay, and I'm just going to fix this really quick right here so that it's fixed. Okay, there we go. Okay, so I'm then going to say I cannot use the temperature. If you recall, you cannot use the temperature in chemistry unless you turn it into Kelvin first. So we're going to take and use this formula here to convert our temperature. This is the generic formula that we practice with. So we're going to take our 20 degrees Celsius and we are going to add this to the 273.16 and get 293.16. So you must convert every temperature into Kelvin by using the formula Kelvin equals degrees Celsius plus 273.16. So I've labeled things. Now I write my generic formula. Remember, this is a formula where we have V's and T's equals V's and T's, but my V and T subscript numbers are different than each other, and that is supposed to be the case. I plug in 2 liters times T2, which is what we're solving for, equals V2, which is 1 liter times T1, 293.16 Kelvin. Ladies and gentlemen, to be honest, this particular formula will trip my students up in the past because they're not careful about where they plug their temperatures in. That is partly why I require the generic formula. So if you write your generic formula before you proceed, always double check that you've placed your temperatures in the right locations. It must have T2 with V1 and T1 with V2. And then you must carefully plug in, because you labeled it, each temperature into its proper location. So I've double checked that. Now I say, what do I have 2 of? I have 2 volumes. Check to see if they're in the same unit. They in fact are. Then I can proceed with my math. In this particular problem, our unknown is on the left. So we're going to multiply the 2 numbers on the right and then divide by 2 liters. When I divide over by 2 liters, the unit of liters cancel, leaving me only units of Kelvin, which makes sense because we are solving for temperature. Please pause the video and make sure you can work through this problem and get my answer. Okay, example 10. If you haven't done so, pause the video, try not to look at the screen, and label yourself to make sure you can label appropriately. So I have 600 milliliters, that's my V1. At 20 degrees Celsius, that's my T1. I want to know what's the volume when the temperature gets to 60 degrees Celsius. So every degree Celsius temperature must be used in Kelvin units, so I have to convert both of them. That's what I did right here, and that's what I did right here. I wrote my generic formula, V1T2, remember V's and T's are opposite subscript numbers, equals V2T1. I carefully plugged in my V1, and I very carefully plugged in my T2, which was over here, and then I set that equal to V2 times my T1, which was right here, and then I checked to see what do I have 2 of. I have 2 temperatures. They are in fact in the same unit, so I can proceed with my math. In this case, I'm solving for V2. So on the left, I'm going to multiply my two variables of V1 and T2, and then I'm going to divide by T1. When I do that, units of Kelvin will cancel, leaving me only units of milliliters, which would make sense since we're solving for volume. Please pause this video, work through this problem on your own, and make sure you can get my number. All right, example number 11. Again, if you haven't done so, please label all the parts of this problem. You're looking for pressures, temperatures, and volumes. As I come across, I see 1 liter as my V1, standard temperature. Now, we talked about standard pressure when we did Boyle's law. Now we have a term called standard temperature. This is even easier. Standard temperature is always going to be 273.16 Kelvin, or if you really are bored, you can say 0 degrees Celsius and then convert it into Kelvin. So if you come across the phrasing standard temperature, you're going to use 273.16 Kelvin. And then we're looking for V2 at 333.00 degrees Celsius. So I have a new temperature, a T2 temperature that I must convert into Kelvin. I did that here with the math. And then I'm going to use my generic formula, write that down. Remember, it should be V1 T2 equals V2 T1. Our temperatures don't play nicely with the others, so they always have a different subscript. Plug in my numbers from what I've labeled. On the left, I have liters, V1, and I have T2. And on the right, I have my unknown V2 and my T1. Pause and to say, okay, what do I have two of? I have two temperatures. Are they in the same unit? Yes. If they weren't, we'd have to fix that. Now I'm going to divide both sides by, multiply the numbers on the left first. I apologize. Multiply the numbers on the left and then divide by 273.16 Kelvin. When I divide by that, I will get my Kelvin units to cancel, leaving me only units of liter, which is what we'd expect because, again, we're solving for volume. Like I've said in the past, please pause the video, check through this, make sure you understand what you're doing, and you can get my answer. Like always, you should be showing your generic formula, numbers with units plugged in, and an answer with unit, and then, of course, any grids you would need to do for conversions. Final example that we're going to go through for Charles' Law is example 12. Here I've labeled everything that I come across. So this is my volume and at this temperature, so I made them my ones. I'm looking for T2, and I'm going to see that my new volume is V2 right here. I'm just going to take a moment to make this in a subscript because I didn't catch this when I was designing these notes. And we're going to come up with our generic formula, V1T2 equals V2T1, and I'm very carefully, as I mentioned several times throughout this video, make sure I plug my temperatures into the right locations. So this is my V1, that's here. This is T2, this is T1, apologize, this is T1, so I need to make sure I put it over on the T1 side, but I first have to convert it into Kelvin, which I did right here. So I'm going to take and solve for T2. In this case, because I have my unknown on the left, I'm going to first multiply by numbers on the right, divide this over, oops, I can't do that yet because I forgot to pause and say, what do I have two of? I have two volume units, volume values or units, and I need to get them in the like units. So I have two things of volume, they're not in the same unit, so I must do a conversion grid, that's what you see down here. And this time I decided to convert it into liters. It really wouldn't matter which direction you went, but if the question specifies in your practice, please go to the unit that I ask. So I'm going to take this 8761.33 milliliters. We know there's 1,000 milliliters in a liter. So we're going to take that, multiply across the top, divide by numbers on the bottom, and we get this into liters. So then we're going to substitute that in, and then we're going to do the math. So now when I divide by 8.76133 liters, my units of liters will cancel, leaving me only units of Kelvin, and that's what we'd expect. Pause the video, do the math, and see if you can get my answer. You should have gotten 175.41 Kelvin. Now, let's go back and look at the problems as a whole and discuss what patterns we see. We're going to go all the way back to question 9. All right, so here we see a decrease in volume, and we see a decrease in temperature. So they did the same thing. That's a direct relationship. As one goes up, the other goes up. As one goes down, the other goes down. We call that a direct relationship. Let's look at example 10, see if our pattern holds true. We went up in temperature, right? And we went up in volume. So they are also directly related. So this means that we're discovering that volume and temperature are directly related. Example 10, let's see, what do we have two of? We have two temperatures. We went up in temperature. 273.16 to 606.16, and we went up in volume from 1 liter to 2.2 liters. So those did the same thing. So volume and temperature are directly related. One does one, the other does the same. Okay, looking at example 12, we need to look at like unit to like unit. So we're looking for that pattern. So we went from 8.76133 liters down to 4.432 liters. And our temperature should also go down. We went 345.89 to 175.41. I just saw that I have a label that's wrong here. This should have been T. I just cut and pasted and forgot to change that to a V. So if you wrote that as V2 in your notes, please quickly correct that. Apologize for that error on the screen. All right, so we have now learned that as temperature goes up, volume goes up. As temperature goes down, volume will go down. Thank you so much.